Hi everyone. In this video, I'm going to explain about the transistor bootstrap time-based generator. In the previous video, I have given you the explanation of transistor Miller time-based generator. Now it is bootstrap. In previous videos, we have seen how bootstrap circuit is going to be generated, constructed with the help of simple resistor and capacitor. Now, how the bootstrap circuit can be constructed using a transistor or a BJT is shown here. See, there are two transistors needed for the bootstrap time-based generator, but whereas in the Miller circuit we have used three BJTs. Okay, first stage is emitter follower, followed by amplifier, and then again emitter follower. These are the three stages we have used in the case of Miller circuit. Now, in the case of time-based generator, which is made up of bootstrap, we need two BJTs Q1 and Q2 as shown here, whereas the first transistor Q1 is applied with the input voltage. First transistor Q1 is applied with input some gating pulse. The voltage which is applied at the input of this bootstrap or Miller circuit is nothing but gating pulse, that is the output of any type of multivibrator. So the time is indicated by TG, gating pulse with a period TG. In this period it is having some low level voltage. Now the transistor Q1 is said to be always in on state, is in saturation region, because it is having the sufficient voltage from VCC. Actually, there is no connection from base to ground. From base 1 to ground, there is no connection. When a negative going pulse is applied, as the capacitor is there, it takes some time because it is a sudden change in the input. It takes some time to charge and gives the output. Meanwhile, the current which is coming from VCC through this resistance RB that goes into the base 1 of the transistor Q1, then Q1 goes into saturation. So under quiescent conditions, we can say the transistor Q1 is operated in saturation region, on nothing but saturation region. Now, the output of the first transistor Q1 is applied as the input of the second transistor, as well as the voltage across the capacitor. The voltage across capacitor, this is the capacitor we are using for time-based generating circuit, nothing but for sweep circuits. So the voltage across this capacitor is VC. This VC is the voltage, output voltage for the transistor Q1. Now, when the transistor Q1 is said to be in saturation region, what is the voltage from collector to emitter? From here to here, we will be having VCE sat. We can say it is VCE sat. So, this VCE sat is the only voltage appear across this capacitor. So, that's why VC, we can write it VC, voltage across capacitor, as VCE sat when the first transistor is in saturation region. Now, the output of this first transistor is connected to the input of second transistor. Second transistor, now it is acting in emitter follower condition. See, there is no component connected from the capacitor. So capacitor is directly connected to VCC, and emitter through which we are taking the output. Here we are taking the output V0. So the overall voltage of the bootstrap circuit we are taking from the output V0, which is from the emitter of the second transistor. That's why it is known as emitter follower. So the second stage is emitter follower. Okay. Now the current entering into this base of the Q2 is IB2, which is coming from this VCC diode and then R, and then towards this B2 and as well as towards this IC. Okay, the current which is coming from VCC through the on diode, or diode is always said to be in on state, because the p-type terminal of the diode is connected to positive supply VCC, and n-type terminal is connected to the other end. So diode is said to be in on state, and when it is in on state, the current coming to this junction and it goes towards this resistor R and enters into this junction. When this transistor Q1 is in on state, the current goes towards this transistor as IC, and the second transistor is in conduction. Second transistor is in conduction because it is having some limited amount of um, voltage, minimum voltage required for the transistor to be in conduction. So a small amount of current that also flows through this IB2. Now if you see the output waveforms, see this is the input waveform what I said. It is a gating waveform applied at the input of first transistor's base. When this input waveform is applied to the first transistor, these are the changes that we are seeing at the output. Okay, generally these changes we are measuring from the output of capacitor, but it is an emitter follower. It gives the unity gain. See, we are saying that the output V0 here, what I have shown, V0 is equal to the input VC. This is the input VC. Listen clearly. This is VC applied at the base of the transistor Q2. This VC is almost appeared at the output as V0. That means V0 is equal to VC because emitter follower is having a gain of unity. Emitter follower is having a gain of unity. That's why there is no change in the input and output. Okay, so V0 is equal to VT. So whatever the changes that we can see across the capacitor, the same changes we are also observing at the output across this resistance RE. That's why this is the output voltage V0, and we can also say that it is the output voltage nothing but across capacitor VC. Okay, so until and unless we are applying the gating pulse, it is the capacitor is no way charging. When we are applying a gating pulse, what happens, which is a negative gating pulse, then the capacitor starts charging. Capacitor starts charging because that negative gating pulse makes the transistor Q1 off. Until the application of gating pulse, the transistor Q1 is in on state, so it is in saturation. Whatever the charge accumulated previously, the capacitor is in discharging in that period. But when a negative gating pulse is applied, Q1 comes into off state because the negative pulse makes the transistor off. Then the capacitor charges. So the charging path is nothing but IR, resistance, and then capacitor C. So RC is the time constant. So now capacitor is having a charging path. It charges, and it tries to charge up to VCC. But when it charges up to the cut-in voltage of this transistor Q2, automatically it maintains some constant voltage across switch. So it maintains the same voltage for some period until the gating pulse results back. So when the gating pulse reverses back, the capacitor with the transistor Q1 comes into on state, so the capacitor again discharges. So charging period is known as sweep period and discharging period is known as retrace period. Okay, overall this particular thing will be happen in the period of TG. Okay, so this is about the explanation of the time-based generator in the Bootstrap using BJT. Now the voltage V0, output voltage V0 is equal to VCE sat minus VBE2. V0 is equal to VCE sat minus VB2. How we have got this one? See, V0 is the voltage from emitter to ground. V0 is the voltage from emitter to ground. What is the voltage at the input of the base? It is VC. Okay, VC is nothing but when the transistor is in on state, Q1 is in on state. What is the VC? VC is equal to VCE sat. And what is the voltage, cut-in voltage across this transistor? It is VBE2 because for the second transistor it is VBE and it is second transistor 2. So when you are taking the voltage at this particular emitter, the voltage appeared at emitter is the difference between these two. So VC minus VBE2, nothing but VC sat minus VBE2. Okay, in that way we have got this expression. Okay, now the current IR, the current IR is equal to, what is the IR? IR is the current coming from VCC towards the junction. This junction is connected to three different components, two transistors Q1 and Q2, and as well as a capacitor. Okay, so IR is divided into two currents, IC and IB2. IC1 and IB2. So when this transistor Q1 is in on state, IC1 current flows through this Q1, and when this transistor Q2 is in conduction, some IB2 also goes towards the base. Then IR is divided as IC1 and IB2. So IR is equal to IC1 plus IB2. Since the base current Q2, that is IB2, is very small compared to this IC1, so we can neglect IB2. IB2 is very small compared to IC1 because the transistor Q1 is in saturation. So saturation transistor draws more current compared to the conduction transistor. That's why IC1 is very high. So we can write IR is equal to IC1. That is equal to VCC by R. So VCC is the maximum voltage, VCC by R. Next up. So for Qn to be really in saturation under quiescent condition, its base current IB1 is equal to, for Q1 to be in saturation, its base current IB1 is equal to, what is IB1? VCC by RB. Where IB1 is coming from? See, IB1 is coming from, there is no component here, I said already. So IB1 is the current that is coming from RB. Okay, that means there is no supply here. So when there is no supply at the input, IB1 is the only source appeared at the base of the transistor Q1 is VCC. That is nothing but the VCC gives a current to the base, then IB1 is going towards the base one. So what is IB1? We can write it as VCC by RB. Okay. It must be, and this current must be at least equal to IC1 by HFE. IC1 by HFE. That is VCC by HFE into R. What is IC1? We have calculated VCC by R. So if you substitute here, VCC by HFE into R. Okay. So the condition is so that VCC by RB must be having a value greater than VCC by HFE into R. So if you simplify this, we will be having RB, VCC gets cancelled, RB goes this side and HFE into R goes onto the left hand side. So RB is less than HFE into R. This is the condition required for the Bootstrap time-based generator to be designed with a BJT. So the input resistance, we are taking the base resistance must be less than the current gain HFE into the resistance R, which is used for the capacitor to charge and to charge as a time constant. Now let us see how a sweep is going to be formed. Formation of sweep. So formation of a sweep. So when a negative gating pulse is applied, I told you already, when a negative gating pulse pulse is applied. Until this part we have discussed now. Now when a negative gating pulse is applied to the first transistor Q1, Q1 comes into off state. Okay, so when Q1 comes into off state, what happens? The capacitor is having a path to charge. Whatever the current that has been going towards the Q1 previously, now it goes towards the capacitor. Here, see, when the transistor Q1 is in on state, IC1 goes towards this one. But when it is in off state, definitely the current enters into the capacitor, so the capacitor charges. Then sweep is starting. So when a negative gating pulse is applied at base of Q1, then Q1 goes into off state. So the capacitor charges. Capacitor charges. So voltage across capacitor VC is equal to 1 by C integral IC1 dt. That is equal to 1 by C integral. What is IC1 VCC by the resistance is R into dt. So VCC R both are constant. So integration gives T. So VCC T by RC. This is the voltage across capacitor VC. So I already told you emitter follower is having a unity gain. So assuming unity gain for emitter follower, nothing but second transistor configuration. Emitter follower. So V0 is equal to, we can write it as VC, that is equal to VCC by T into RC, product of resistance and capacitance. Okay. Now, if the output V0 reaches the VCC in time Ts less than Tg, if the output reaches VCC within the time Ts less than Tg sweep time, then VCC is equal to VCC into Ts by RC, or we can write it as Ts is equal to RC. What do you mean by this line? See, if the output reaches VCC means capacitor charges. Capacitor charges. When capacitor starts charging, see, when capacitor starts charging, actually capacitor has to charge up to VCC plus VCC. Suppose within this particular period where Ts is less than Tg, only in this particular period, if the capacitor is able to reach up to this VCC, then Ts we can write it as Ts is equal to resistance into capacitance. That is the meaning of this one. So within the gating pulse, if it reaches the particular value, we can write it as Ts is equal to R into C. So that the sweep voltage Vs, sweep voltage Es is equal to VCC into Tg by R into C. So whereas if the sweep amplitude Vs is less than VCC, then the maximum ramp voltage is given by like this. Vs is equal to VCC into Tg by Rc. Okay. So this is till now we have discussed. See here, we have divided the entire input waveform into different parts. This is the first part we have discussed. Okay, that is under normal conditions how the transistor Q1 and Q2 are acting. Later, when when gating pulse is applied, Q1 comes into off state, so capacitor charging and it holds for some period. After that, when gating pulse is reversed back, then capacitor has to discharge. capacitor has to discharge. We have discussed until this particular point where the capacitor is charging. So once it goes back, the capacitor discharges. That period is known as retrace period or retrace interval. Okay, so that retrace interval and the recovery process we will discuss in the next video. Thank you.